All right, now that we finished our long intro to buffers, let's actually do some buffer problems. If you look at arginine down here in question 17, you're told the 3 pKa's. Now what this means, everybody, I can design a buffer using just the arginine and its conjugate partners to have a buffer near pH 2.2 or 9.0 or 12.5. I can design 9 buffers. 9. I can have one exactly 2.2 by having equal amounts of the acid called pKa1 and its conjugate base. I could have pH 2.1 by having just a little bit more of that acid than the base. Are you with me? Or I could have a 2.3 by having a little more base than acid. But it would be this acid, pKa1 acid. If that acid's proton isn't around, then you're moving on to pKa2. Where that acid has a pKa of 9, you can make a buffer 8.9 by having a little more base than the acid. You can have 9.0 by having equal amounts. You can have 9.1 by having a little more base than acid. Now you guys take it from here. How can I do a 12.4 buffer? I'd have to have this pKa acid, and I want 12.4. So do I need more of the acid or the base? I want 12.4, which is below acid's lower pH. So I need more of the acid, a little more, a little. And if I want a perfect 12.5 buffer, what do? Make sure I have equal amounts of pKa3 proton present and its conjugate base. If I want 12.6, I need more of the pKa3 acid, I need more of the conjugate base of the pKa3 than the pKa3. Okay? So yes, I can make any of these 9 answers the correct answer just by changing this one number here. We're doing a titration. So in this problem, we're going to start with a fully protonated form of arginine. You're not going to end with a fully protonated form, because after the first 2 moles of, what's the base called? I'm listening carefully. What's the base called? I need the name of the base in this problem. I don't want to hear that first word. It's not the base. Hydroxide. I have developed selective hearing and reading skills now. I don't even read potassium in this question anymore. I know it's what job is the potassium? Spectator. Please stop thinking about spectators, right? It's like an athlete going to a game. If he's thinking about spectators, guess what the outcome's going to look like? No, he's focused on the game. All right, hydroxide's the game. So we're going to do what's called an ice problem. You ready for it? Some of you are cringing. This is an easy ice, not like 141 with your quadratic equations. That's 142, sorry. Some of you, this is brand new. I stands for initial, C stands for change, and this is not even treated like an equilibrium problem. E just stands for the end. Okay, these are weak acids and weak bases. We assume they kind of stay the way they are. They're weak. They don't react very much. So your base is hydroxide. How many moles of hydroxide did you start with initially? No, moles of hydroxide. 5.1. And what's the name of the acid? Fully protonated. Watch this. Watch. Where the heck did that come from? Look, that's not in the question. Wait, what? No, don't look for A over there. Don't be looking on the periodic table. This is a generic triprotonated acid. Question 1. How did I know I didn't want H4A or H6A or H9A? Please read question 17 and tell me how many pKa's there are. 3. So in the fully protonated form, how many acid protons are there? Say it again. 3. Good. So the fully protonated form has a generic formula of H3A. Got it? If I gave you 4 pKa's, what would you be starting with? 4 H4A. If I gave you 2 pKa's, you start with H2A. Okay, good. All right, H3A. What do bases do to acids? Do they take protons off of them or put protons on them? They remove protons. Acids give protons. How much H3A am I starting with in moles? I know I don't have it on the screen anymore, but you guys have it in front of you. 2 moles. Rules of chemistry have not changed since you took 141. After the 2 moles of H3A are reacted, this reaction is over. Ice number 1 will be over after 2 moles is reacted. What does hydroxide become after it picks up a proton? H2O. I like the way you said that. H2O. And I always like writing this statement, but it's kind of silly. Who cares? Water does not affect this problem at all. It just dilutes things. It doesn't change the ratio of acid to base, does it? Isn't that equation log of pH equals log of A minus over HA? That's an acid to base ratio. Changing the amount of solvent won't change it because they're both in the same solvent, right? Okay, so I write who cares for the ones that aren't acid-base partners that are of concern. What happens to H3A is very important. What does it become? You removed a proton. What's left? H2A minus, not 2 minus. Start as neutral, you're taking away 1 proton at a time.
Will we get in person like that if we don't put A?
I don't need to see A at all, but some kind of short form helps, right? Oh, you could just draw out the fully protonated form here. Just draw it out. You guys do know that you learned from your first test, time is a big issue, right? You don't want to be writing this instead of H3A, do you? No, I don't either. Okay. All right, so the change, well, what's the most reaction you can have up here? Which one's the limiting reactant? It will react completely. H3A reacts completely. Also getting rid of 2 moles of hydroxide as it does so. Creating, who cares how much water? I'm not even going to write it down. It's 2 moles. Who cares? But the important thing is you created 2 moles of H2A minus. The important thing is H3A is gone. You're no longer concerned about pKa1. It's over. All right, 3.1. Pretty soon you're going to figure out you don't even care about pKa2 in this problem. Why do I not care about pKa1? Of these 3 numbers, which one of them has the most protons? Don't even look at the structure. Which one of the numbers corresponds to the species that has all of its protons? The first one. It should make sense. The most protonated one is the strongest acid. Okay? Then this one is the next one, isn't it? Yeah. I don't have any H3A anymore in this problem. It's not a discussion item. All right. So ice number 2 is starting. Start all over. You still have hydroxide. You are not done any buffer problem until you've reacted completely the strong base, as in this buffer problem, or the strong acid, as in question number 17. You must react your strong base or strong acid completely, or your buffer problem is not done. So we got to get a hydroxide to 0 before we're done. It won't even be done after this ice problem, will it? What's it reacting with now? H2A minus. I'm going to write water, but I don't care. What did H2A minus just become? No, you're not putting protons on here. You're taking protons off. Please stop adding protons. HA minus 2 or 2 minus. We don't care. So we started with 3.1 hydroxide. We made 2 H2A minuses in the previous ice. We don't care about water. We had 0 HA negative 2s. Same limiting reaction. Well, it's a different species this time, but it's So when you're done, you have 2 of this, 0 of that, 1.1 of this. We're still not done, are we? No. So ice 3 is the next one. It's the end. You know how you know it's the end? Hydroxide will be what number when we're done this one? 0, and you're finally done. What species did you just create by taking the last proton off HA -2? What species did you create? There's a pattern on the right side of the screen. You can just use that to answer. A3-. Started with 2 moles hydroxide. No, 1.1 moles hydroxide. Wait, we have a new limiting reactant. Are you excited? Should be, because it's hydroxide. So how much do you lose hydroxide? Don't say 2. Yeah, live in reality, people. You made 1.1 of the base. You're left with 0.9 of the acid. Do you agree? And you're done. You put a happy face when hydroxide goes down to 0. You don't have to. But there you go. That's when you know you're done. I'm not even going to write the Henderson-Hasselbalch equation. That's the first time I've said the names. That was the one where pH equals pKa plus log of base over acid. We have 2 species here. I'm circling the species and how much there is. The species and how much there is. Which one is there more of in this pair? The acid or the base? Yes. Sorry. There's more A3-, the base, than the acid. What happens to a buffer when you have a mixture of each? The pH is close to pKa. More base than acid. pH a little above pKa. Did I use a calculator? Did I have to? Isn't this the best way to learn stuff? No, I think so. pH, here's my short form. pKa with an up arrow. Why? Why up arrow? More base than acid. Explains why the up arrow. Now pick which of the multiple choice answers has the right one. Please don't use pKa1. Do not do it. There is no this is pKa1 right here. This is pKa1. Bye. pKa1. Is there any of this molecule around? No. This is pKa2. Is there any of this molecule around? No. There is this molecule around. 3. What's the number? 2.2. Yeah, there's a typo in my questions. I don't know how that typo got by me. All my answers are centered around pH, and I forgot. I goofed on the first one, didn't I? Just fix the answers. Those answers aren't even relevant. You know that, right? But if you want, I want to be consistent in each of my 3 sets of answers. The middle one is always pKa. Will be on your test too. There might be 4 of them. There might be 6 of them. They're all centered on pKa. Okay. When you have more base than acid, then you pick the correct pKa, which was 12.5, correct? And I want the only answer that's a little above 12.5. Yeah. It's answer AE 12.6, correct?
Wait, can you repeat how you got to that?
Well, I have to be close to 12.5 because that's the pKa of the acid in this buffer. Do you agree? I have to be close to 12. We got to step by step for answering your question. Find the right pKa first. Don't choose pKa 1 or 2 because that acid doesn't exist here. The only things that exist are circled in red. That's the 3rd pKa there. You got to be close to 12.5 because it's a buffer problem. Why are we above it? Because you have more of the base than the acid. There's that good story. I think that's another video. Wow, we're gonna have 3 videos. Oh.